So we'll discuss a few examples in this lecture. So let's say that we have a system which is of the form this. So we are taking a scalar system. So what you have is G is something that maps from R to R. G is local Lipschitz in the set minus A to plus A. G at 0 is 0 and alpha G alpha is greater than 0 for all alpha not equal to 0 and alpha lying in the set minus A to plus A. Okay, so what we want to know is the following: is origin asymptotically stable? This is what we want to know. Okay, so the domain that is given to us is minus A2 plus A, which is of course a subset of the real numbers, and what we have 0 is a equilibrium point for the system under consideration because x dot is 0 for x equal to 0. Okay, now we have to find a Lyapunov function that maps from V to D, and we'll have the property that it is 0 at 0 and is greater than 0 for alpha not equal to 0 and alpha in the domain D. So one such Lyapunov function that you can think of is v of x to be equal to 0 to x g of y dy. Okay, so this is the Lyapunov function that you can choose, and you can verify that when x is 0, v of 0 is 0, and when x is not 0, for that v of x is going to be greater than 0. So v is a positive definite function, and this is continuously differentiable because g is locally Lipschitz. Okay, now so this function satisfies the properties that are needed for v to be a candidate for a Lyapunov function. Okay, so it is a valid Lyapunov function candidate. Now when we do dv by dt, this is nothing but del v by del x x dot. Now what is del v by del x? From here it is g of x, and x dot is nothing but minus g of x. This gives me, this is minus g of x squared. This is 0 only when x is 0, and rest of the time it is negative definite negative. So which means that v dot that you have got, which is dv by dt, is strictly less than 0. Okay, so this is less than 0 for all x in this set, and this is v dot, and v dot is 0. Sorry, I'll write it like this: v dot of 0 is 0, right? So from here what you see is we have a positive definite function whose derivative along the system's trajectory is negative definite, and hence what we have is origin is asymptotically stable. Okay, so the main idea here is to basically come up with this Lyapunov function. Now note that if you have a Lyapunov candidate function v that is positive definite, but v dot does not turn out to be negative definite. In fact, v dot does not turn out to be negative semi-definite as well, or better, v dot turns out to be indefinite. Then it essentially means that with the help of that Lyapunov function, will not be able to conclude about the stability of the equilibrium point. Okay, so the Lyapunov theorem is just a sufficient condition. It just says that if you can find a Lyapunov continuously differentiable positive definite function, which is basically a Lyapunov candidate function, whose derivative along the system is negative semi-definite, then the equilibrium point is stable, and if the derivative is negative definite, then the equilibrium point is asymptotically stable. Okay, it does not say anything beyond that. It doesn't. So if you are not able to find such a v, I mean, if you find a positive definite v, but v dot turns out to be sign indefinite, then well, you cannot conclude anything about the stability. Okay, let's move on to another example. Suppose you have a system which is theta double dot is equal to minus g by L sine theta. Okay, if we set x1 to be equal to theta and x2 to be equal to theta dot, then x1 dot is x2 and x2 dot is going to be minus g by L sine of x1. That's what we have, where x1 and x2 both belong to reals. Or rather, I should put it like this, where x1 belongs to the set minus pi to pi, and both extreme points excluded, and x2 belongs to reals. So the state vector x, which comprises of x1 x2, is in the set D, which is defined as minus pi to pi cross R. Okay, so x1 takes values from the first set, x2 takes the value from R. So this is what we have. Now we need to form a Lyapunov candidate function that maps D to R. So one such function is g by L 1 minus cos x1 plus half x2 square. So you notice the first term here is the potential energy function, and the second term here represents the kinetic energy function. Okay, so if you take a derivative of v with respect to t, what you get is g by L x1 dot sine x1 plus x2 dot. Now x1 dot is x2 and x2 dot is minus g by L sine x1. So if you substitute the value of x1 dot and x2 dot from the system dynamics, we get that v dot x is going to be 0, and this is going to hold for all x in the domain D. Okay, so v dot is essentially negative semi-definite. Equal to 0 means it is satisfying the inequality less than equal to 0 as well. So in such a case, we can conclude that origin is stable. We cannot conclude origin is asymptotically stable or not. Now, since this is the equation of a pendulum, and origin means that the pendulum is vertically down and is at rest. Okay, so if you start at any other point other than this particular value, you see that the pendulum will have sustained oscillation. So the total energy does not decrease, and that is what is also being seen here. Okay, so the total energy is not decreasing. Okay, now let's modify this pendulum equation, and let's say that we have it in the form of theta double dot is minus g by L sine theta minus k by m theta dot. Okay, all the coefficients that we are considering are positive constants. So again, we can set the states x1 to be theta and x2 to be theta dot. So we'll have x1 dot to be equal to x2, x2 dot to be equal to minus g by L sine x1 minus k by m x2. Okay, and the state vector x is nothing but it comprises of the states x1 and x2 that belongs to the set D, which is from minus pi to pi, both excluded, cross R is the set. And let's say that we choose the Lyapunov function which we had chosen earlier, which was g by L 1 minus cos x1 plus half x2 square. With the derivative of this, what we get is g by L x2 g by L x1 dot sine x1 plus x2 dot. Now if you substitute the value of x1 dot and x2 dot in the equation of v dot of x, what we get is of the form minus k by m x2 squared, and this is less than equal to 0. Basically this is negative semi-definite. Okay, for and in the domain D. So from the chosen Lyapunov function, we can only conclude that origin is stable. We cannot conclude about asymptotic stability. Okay, but what you see here is with the term minus k by m theta dot that acts as a damping term, the amplitudes of oscillation for the simple pendulum will slowly die, will keep on dying out, and finally it will reach, it will go towards origin asymptotically. Okay, so we from the system and our experience with the system, we know that origin is going to be asymptotically stable, but with the chosen Lyapunov function, the only thing that we can conclude is origin is stable, because what we have is v dot to be negative semi-definite, not negative definite. Okay, so as you see here in this particular example, with the choice of Lyapunov function, okay, with the choice of the Lyapunov function, our conclusions get limited. Okay, so in this case, we were expecting we would get origin to be asymptotically stable, but with the choice of the Lyapunov function v, we can only conclude that the origin is stable and not asymptotically stable. Okay, so you will get some assignments on the stability problems. I suggest that you try solving them and see how you can conclude about what you can conclude about stability with Lyapunov functions. I would also suggest that though in most of the assignments we'll be telling you what is the Lyapunov function that you should choose, but I also suggest that you try to construct Lyapunov functions on your own. The Lyapunov function here, I mean this method here also helps us in designing controllers. Okay, so if you want, let's say, origin of a system to be globally asymptotically stable, then we can design our controller such that this happens. And this is basically done how? So what we have been observing here is we once we construct a Lyapunov candidate function, we take a derivative of the function. Once we take a derivative of the function, the dynamics of the system appears. So when you substitute the dynamics, the control input term, if present, will also appear. Now it is the designer's job to set the control input such that the origin becomes globally asymptotically stable, which means you have to start with a radially unbounded V, and you have to come up with a controller such that V dot becomes negative definite. Okay, and with the choice of U, you have to ensure that the system has origin as the only equilibrium point. With this, you can essentially come up with a control structure that makes origin as a globally asymptotically stable equilibrium point for the closed loop system, right? So with these three examples here, I'll stop here, and I says that again you go through the assignments that have been given to you and solve those questions. Thank you.